So I'm here at the University of Oxford today, and I have been challenged to do some A-level maths. So I'm here with Tom Rocks Maths. Tom, who are you?
Who am I?
Yeah, sorry, who are you? Yeah, who are you?
As I said, I have a channel, Tom Rocks Maths. I also teach maths here at the University of Oxford, which is why we're here in this beautiful old library at St Edmund Hall. This is the college where I teach. And Lewis challenged me to do some physics originally.
I assumed having a big channel looking at A-level maths and other, university level maths, I just assumed you'd have done physics, but you hadn't.
I hadn't done A-level physics. So when Lewis discovered this, he was like, right, I'm going to come to Oxford and give you some physics questions. So
if you want to see how Tom got on that, there's another video where he did an A-level physics paper. But I guess returning the favour, you're going to challenge me to do some A-level maths, aren't you?
That is... I am relishing this opportunity.
And here's the thing, right? So when I was at school, I liked A-level maths. I did further maths as well. And that was over 23 years ago. So I did my A-levels in 2000, which is older than most people watching this video, which makes me feel so old. So we're going to do some maths questions.
We are.
I did say, could we do some like mechanics-y ones? But
I have...
Yeah.
Lewis was very nice to me and gave me mathematical physics questions, as some of you may know if you've watched that one. So I have also felt I would be quite nice.
Yeah.
And I've actually brought them along in hard copy, as I know that in your usual videos you tend to write on paper.
Yeah, I think paper is... I mean, you're going to do real exams on paper, but I'm going to be recording my answers on the iPad. But we've got some
but I do have the
physical
questions
old school...
for you to look at. So Lewis hasn't seen these yet. So...
yeah.
Let's see what you make of them.
Okay.
So I thought we would start with a projectile motion question.
Cool.
Sort of a SUVAT, as you have now informed me, is what you would refer to as physicists.
Absolutely, yeah.
So that's going to be the first one here. So this is question 11. Here looking at projectiles. So I feel like, what did we have last time? We had archery in the physics one, and now we've got golf balls.
So standard kind of sporting activities, maybe for the older generation.
Yeah.
Am I part of that now? Maybe I'm part. Yeah. Okay. Right.
Projectile motion.
Yeah. Projectile motion.
Projectile motion. So so we've got. I mean, I'm sure you can obviously read this for yourself, but we've got a ball being hit with some initial given speed. It's initially at a height above the ground. We've got an angle, and then it's sort of giving us various bits of information. I do enjoy this. I don't know if this is offensive to physicists or not, but it says, take the acceleration due to gravity to be 10 meters per second squared.
I see, that bothers me. It's like a GCSE level kind of questioning. But okay, we'll go with 10. Yeah, that's fine. Okay.
So the first thing I want you to work out there is time taken for the ball to travel from the start point to the end point.
Right, so as normal, I'm just going to start with the diagram, I guess. So this is kind of what it has in the exam paper. It's not brilliant, but we've got position A over here and position B. And we want to find the total time. Now in the question, we know how quickly it's initially moving. So I'm going to, again, just draw on this. It's not the best diagram, but it's really for me, it's like, this is how I guess I'm kind of copying that, and I guess I could annotate that, but I think for me it's just nice to know the numbers. So we've got 25 meters per second.
I do the same. I always draw my own diagram.
Yeah, and that's at 15 degrees above the horizontal. But also it's going to drop down through 4 meters.
Yep.
Okay. Right, the first thing I've noticed here is that it just says 4 meters. Now in physics, we tend to use like 4.0 or 4.00, and 4 meters to me looks like one significant figure.
Yeah.
Is that normal?
In maths, we would just take 4 meters to mean exactly 4 meters.
Okay. Right. Okay.
But
so
I believe this is something that I have only myself recently learnt, as of course I teach university maths, but I have spent quite a bit of time, and you may have seen some of the videos of me doing A-level maths papers.
Yeah.
And it turns out that I believe the standard thing is to give all your answers to 3 significant figures. But so I would recommend... So if you would like to treat 4 as 4.00...
Okay, and I will say that's 25.0 meters per second.
Yes.
Oh, there's something that just doesn't sit well with me. But okay, so we've got some stuff here, and the time taken to go from A to B. Now, I would say the time it takes to go horizontally from A to B is going to be the same as the time it takes to go up and then back down again in the vertical direction. So my approach would be, is because it's projectile motion, I'm going to write down that.
Okay.
And then I'm going to say in the vertical directions, let's say downwards is positive, just for my kind of system. So it starts at A and it goes down 4 meters to B. So the vertical displacement is 4 meters.
Yep.
The initial velocity, so we've got, I'm just going to do that a little bit bigger here. So that's 25.
Yep.
And that's like the I'm going to change that colour to red. So that's kind of my hypotenuse. We then have like the horizontal and like vertical component of velocity.
Yep.
And if we know that this angle here, theta, is 15 degrees, that's my theta, this is going to be the adjacent side and that's opposite.
Mm-hmm.
So I've just kind of, I probably didn't need to do that, but for me it's like, takes like 10 seconds.
Mm-hmm.
And so now, if we want to know the opposite side, that's going to be the vertical component of velocity. So that's going to be sine, because we know h, theta, and opposite. And then it's, we talked about this in the last video, didn't we? Sokotoa. I said silly old Harry couldn't afford his tired old alligator, which I always say in my head. I don't say this out loud. And what's yours?
Silly old Harry caught a herring trawling over America.
Okay, so basically, silly old Harry is what we're going to use.
Yeah.
So this side here, the opposite side, is going to be equal to 25 times sine of 15.
Mm-hmm.
Now I could work it out, but I'm just going to leave it like that to kind of be a bit more exact. In the vertical direction, we don't know how quickly it's going at B, so that's an unknown. The acceleration is... Oh no, actually, hold on, I've made a mistake there. If it's going upwards initially, and I've said downwards is positive, then that's going to be minus, isn't it?
Yeah.
So it's like a minus up.
Yeah.
So it's like, minus up is down. And then A, this pains me to write it, is 10. And I'm just going to put the units in there just to kind of... There we go. Right. And what we want to know is the time. So we know S, U, A, and T. And I would say from the Suvat equations that S is equal to UT plus a half AT squared.
Yeah. I wouldn't know that off the top of my head.
Would you not?
But
Okay.
I think it's fair. I mean,
yeah.
I think as a physicist, you know this equation. It is a true equation. So I am going to say I'm happy for you to state that.
Now the thing is, we know S, we know U, we know A, but we don't know T. But we can't really rearrange it to make T the subject because we've got a T and a T squared. So my approach, it's only worth 3 marks, isn't it?
Yes.
Right. I'm going to do an intermediate step and I'm going to work out V. Okay? Because if I know V, I can then use another equation to work out T.
Okay.
So we know that V squared is equal to U squared plus 2AS, which is another Suvat equation without time in it.
Okay.
So that means V is going to be equal to U squared, which is minus 25 sine 15, and that's squared, plus 2 times A times S. Is that right?
Yeah, that's going to be squared rather than just V, I think.
Oh yeah, so that's going to be squared. So sorry, we're going to work out V.
Square root at the end.
Do you know, it's really difficult to do like a straight line. Okay, so hopefully you can read that.
Yeah.
Now, you didn't use a calculator much in the video, did you? You were like, yeah, I'll eyeball that. It's roughly about this. I'm going to...
You are allowed a calculator in this exam, so again, I will permit the use of the calculator.
Okay, so this is just a normal, like, standard scientific calculator. Nothing, it's not graphical. It's just like, it does sine, cos, and tan. That's pretty much what it does. So we've got that plus 2 times 10, so it's 20 times 4, so plus 80. And then if I square root that, we find V is 11.03934. Okay, now I'm writing it down like that in case, because that's not my final answer. That's going to be used again. Okay, is that making you squirm as a mathematician?
No, I'm very intrigued as to how many significant figures you chose.
Okay.
I would have gone for 11.04 and been like, that's definitely going to be enough, but that's...
What I don't want to do, I don't want to, like, round down too early.
No,
and then have that kind of magnified later, maybe in another question.
Yep.
Okay, So now we know this. T, well, we can say that V is equal to U plus AT, which is another Suvat equation.
Mm-hmm.
So T is equal to V minus U divided by A. Okay, so we've worked out V up here, 11.03934. It's probably overkill. I think, yeah, 11.04 is fine. We're going to take away the initial, so that's take away minus 25 sine 15.
Yeah.
And divide that all by 10. So that's the same as adding, isn't it? So that's just plus 25 sine of 15. 17.5 divided by 10 gives me a time equal to 1.75 seconds.
And that's with 3 significant figures, isn't it? And
Yeah.
that is exactly
Is it?
what they were looking for, yeah.
Okay, so there must be an easier way, because that's like, that's more than 3 minutes worth of work. I mean, again, if it was a physics paper, I would say, well, that's equal to 2 seconds. That's to one significant figure.
Yeah. So I think, again, having had a quick look at the mark scheme, you were allowed to use the equations.
Yeah,
So,
okay.
So again, that actually surprised me, because as we saw in my physics case, I was deriving these equations because I personally didn't know them. But
From like first principles.
Yes.
And you got them correct as well. This is the amazing thing. But it's like,
yeah.
so okay, so say we took this one here then.
This is where you would then go from. So this is what you did slightly differently.
Okay.
The mathematician would get this one in S equals UT plus a half AT squared, sub in all the values, get a quadratic in T, and then use the quadratic formula.
Okay.
So the classic.
So I think I use a quadratic
minus
formula.
B plus or minus root B squared minus 4AC over 2A. Did use the whole quadratic formula.
Okay, so that's not the way I'd normally approach it in a physics lesson, because I suspect most physics students, they're doing A-level physics, most people are doing A-level maths as well. Mm-hmm. They're probably familiar with the quadratic equation. I cannot remember the last time I used it since leaving school. Maybe I used it at university. Since I left education,
You always have to solve a quadratic.
no, you don't. No, you really don't. Once you leave academia,
It could have saved you some time. I
have,
like the way that you got around it, though. I did think that was nice,
Yeah.
because given that it's clear that you are allowed to use the Suvat forms and you obviously know them, I think that was a nice way around it if you weren't confident in your ability to remember the quadratic formula.
Yeah, so I think that's not an elegant way of doing it. It's not the most efficient, but it will get to right. So using a quadratic formula, you put the numbers in and then you do a bit of rearrangement. Okay, should we move on to the next part? Right.
Determine the horizontal distance of B from A.
Okay, so for this one, we want to know, that horizontal distance along there.
Yep.
Right. Okay. But we know the time, don't we? Because that's what we worked out.
Yeah.
And so if we know the time it's taken, and we know its horizontal component of velocity, is there any air resistance in this?
No.
So it's just a model. Yeah, so it's modelled as a particle moving under the influence of gravity. So there's no friction.
Yep.
Air resistance is negligible. Excellent.
Classic.
So so for
borrowing from the physicist for that one.
Yeah. So for this one, I'm just going to use probably like it's kind of like the probably the simplest equation, that speed equals distance over time.
Yeah.
So speed equals distance over time, or v equals s over t if we're looking at velocity. Mm-hmm. In the horizontal direction, so I'm just going to put an arrow there. We're going to ignore it, the fact it's going up and down. The displacement is equal to its horizontal velocity times the time. And the horizontal component of velocity, which is the adjacent side, and that's the COF from Sokotoa. So that's cos, isn't it? Yep. So it's going to be 25 cos 15, and that's how quickly it's moving.
Yep.
Multiplied by the time of 1.75 seconds, and that's how far it goes. So, as a physicist, I'd probably keep the number in my calculator from the previous step. So
I'd have pressed clear already.
Oh, really? I mean, so I'd be saying that whatever I've calculated to begin with, I'm going to keep the answer. So I'm going to keep it here. I'm going to multiply it by 25 cos 15.
Yeah.
And this gives me an answer of 42.2829. So that's 42.3 meters. And I've given that to 3 significant figures.
Yep.
How's it?
Perfect.
Good?
Yeah. That's
cool.
5 out of 5 so far. Yep.
Right. That felt more like a 2-mark question.
Yes.
Because there seemed to be 2 points. Like, not like what I did before. Okay.
4 marker. Direction of motion of the ball 1.5 seconds after the golfer hits the ball.
Okay, so it's 1.75 seconds for the whole journey. So I'm thinking it's going to be over here somewhere. So we're looking at the ball here. And we want to know the direction it's going in. Like that.
Yeah.
So I suppose then, the direction it's going to be... There's a horizontal component of velocity and there's going to be a vertical component of velocity.
Yep.
And we know, so it's getting a bit messy on this now, but let me draw that out again. So it's got a horizontal component of velocity, which is going to be equal to 25 times cos 15.
Yep.
And the vertical component of velocity, I guess it could be up or down. I'm going to guess it's down, but it could be up.
Yep.
We don't know that, so I'm going to call that VH to be my, like, V, no, not VH, VV. So that's going to be the vertical component of velocity, so that's VV over here. Okay, so in that case, I'm going to use Suvat again, and I'm going to write, again, in the vertical direction, I think last time I said down was positive.
Yeah.
So we don't know how far it's dropped. Initially it was going upwards, so that's minus 25 sine 15 meters per second. We don't know V, so I'm just going to put a question mark there to show that's what we're trying to find.
Yeah.
Downwards, again, 10, and the time, it's 1.5.
Yes.
Okay, so this looks a lot easier than that first part. So again, we can use V equals U plus AT. So I'm going to use the equation that says V is equal to U plus AT.
Mm-hmm.
So U is equal to minus 25 sine 15 plus, it's going to be 10 times 1.5.
Yep.
Is that right?
I think so.
Okay, so let's do it. So 25 times sine 15 is 6.47. I'm taking that away off that, aren't I? So it's 15 minus the answer. Okay, so V is going to be equal to plus 8.5295. Okay.
I'm just laughing in my head. I read your calculator was like 8.53.
Yeah, but then I was thinking, when do I stop? Because I committed to the 9, and then I had to commit to the next one. So that's going to be about 8.53. Okay, and so you've got a horizontal component of velocity, a vertical component, and that bit's going to be like that. So that's going to be the total velocity, and we want to find the direction, don't we?
I said the direction of the motion. Yes.
So we maybe want to look at this angle, maybe. Or this angle. I don't think it really matters which one we choose.
I think as long as you describe it relative to an obvious reference point.
So something from vertical or
is
something
how I
below
would interpret that. Yeah.
Cool.
So yeah, either something from the vertical or something from the horizontal. As long as you clearly explain the
Okay.
direction. Yeah.
So what I'm going to do is, it seems really basic, but I'm going to look at this. That's hypotenuse, that's the adjacent, and that's the opposite, and that's theta. And to work out theta, we know that tan theta is opposite over adjacent.
Yep.
And so the opposite side is what we've worked out, so that's 8.53. And the adjacent side is 25 cos 15.
Yep.
So if we do that, is this what you do?
I think so.
Inverse
I think
tan
so.
of that
No, yeah,
would be,
I think so.
and that means theta, if we take inverse tan of that. What was it? Do you say inverse tan or tan to the minus 1?
I might even say arctan.
Or arctan. Here's another question then, right? Okay, this is not related to this question. You've got a natural log of something.
Uh-huh.
Do you say natural log? Do you say ln? Or do you just call it a log?
I change that on a daily or maybe even hourly basis.
Is that the official line?
That's my... No, I was doing this yesterday in my tutorials, and sometimes I wrote ln, and sometimes I wrote... Or sometimes I wrote log, and sometimes... I don't think I ever say natural log. I either say ln or write ln, but say log. Or I'll just write log.
Okay, cool. That's because I've said different things over time, and it's like,
Yeah.
what do you say? Because ln sounds a bit weird to me. Natural
Yeah.
log is like a big mouthful, but if you've written ln and you're saying log of this, log of that, it kind of makes sense in the context of what you're saying.
Yes.
So
I think if you yourself know what it means, it's okay.
and if,
It's
yeah,
only a problem when there's ambiguity with other people.
cool. So this is arctan of that is equal to 19.454, so that's 19.5 degrees, and that's going to be below the horizontal.
That is perfect.
Is it?
Yeah.
Oh, physics works. Physics works.
Yeah, no, exactly that. Yeah, 19.5 below the
I'm
horizontal.
happy with that.
I thought it felt to me like then your physics intuition about the fact that it would be pointing downwards was kind of helpful in a way.
To be honest, though, if it had been going up, I'd have still written down the same suvat, and I guess it was just thinking, well, if it's 1.5 seconds into that longest journey, it's probably going down. But that's a bit of a guess. So
Yeah,
I guess if I'd done it the other way, it would have given me a negative or whatever it's.
yeah.
Yeah.
I think it would have still worked even if you'd been trying to calculate it as though it was positive. But
Cool.
But I don't know. It felt like as me observing as a mathematician.
Yeah.
It felt like there were like physics cogs turning in your brain about like your sort of real world intuition as to what the answer was going to be. And I don't think mathematicians necessarily always do that.
Okay, cool.
They're just like, it's numbers, let's just do it.
And then just trust the number rather than thinking about what it means.
Yeah.
Okay, what's the last bit then? So I think that's just one more mark, actually, isn't it?
The horizontal distance, from A to B is found to be greater than the answer to part B. So I think you got like 42.3 meters. Apparently it's actually a little bit more than that.
Yeah.
State one factor that could account for the difference. This is a physics question.
So this one here then, I guess there's so many things it could be. It could be that maybe it wasn't exactly 4 meters. Maybe that was that rounding error, but it's not going to play later on. I suppose as well, actually, this just treats it as like a point particle, like this thing that's just moving through the air. Mm-hmm. Whereas from what I do know about golf, which I'm not very good at all, is, the ball's going to be spinning, isn't it? So there might be, as the ball is spinning, there's going to be an effect that's going to give it a bit of extra lift, maybe. So it goes a little bit further. I can't do this myself, but in reality, because it's not just a simple system, it might be going a bit further. Is that spin on the ball?
Yeah.
That's it. So that's one. I guess also it could be windy. Like if you're playing into a headwind, it's not going to go as far as if you've got a tailwind. So it might be that I guess we've got the vector of that ball, but say there's like the wind was blowing at say 10 meters per second, you'd be adding 10 meters per second onto the whole flight of that ball, which is what 1.75 seconds. So if the wind was going at 10 meters per second, that could add like 17.5 meters to the total thing. Yeah. So actually, I like that one. That's like that's a good physics question.
That one is a physics question.
So so far, easy peasy. I don't know what the fuss is about A-level maths.
That one I think that one was the most physics question I could find.
Cool. Okay. Right.
Not in any way. You did very well. I'm genuinely impressed.
I'm happy.
But I think that one felt very like in your safe space as a physicist. Suvat, as you would say.
Yeah. Suvat. That's the safe bit. Yeah. So what's next?
So your next question is going to be number 13. Probably a little bit less physicsy. There's sort of vectors. It does talk about forces and it does talk about speed and distance.
Okay, that's physics, isn't it?
Yeah, I'm glad we agree. But it's in the context of vectors, which is perhaps possibly a bit more mathsy than you're used to.
Okay.
But I guess we'll see, right?
Yeah, let's see how it goes.
Let's see.
And let's see what I can remember.
So you've got two unit vectors, I and j, are in the directions east and north respectively. That's a very physics way of thinking about it. They're helping you out there. I would just be like, I to me is x direction, j is...
So I've never used I and j teaching physics. Okay. So why do we use I and j, not x and y?
Because these represent the unit vector. So if you have a distance x, if you are position x along the x-axis, you would say that's x times I.
Okay.
Or if you had you said a general point in the plane, and you were to call it the point was x, y in the plane, you would say your x times I plus y times j.
Okay.
So I as like a vector would be, I would equal 0, 1. Sorry, 1, 0.
Yeah.
I would be 1, 0, and j would be 0, 1.
Okay.
As like a components of the vector.
Fine. What I do like is the fact they say basically I is east and j is north. That makes sense to me. Okay, but that's good so far.
And units, so they're one step.
Oh, okay, yeah.
Time t seconds, particle mass 2 kilograms is moving on a smooth horizontal surface under the action of a constant horizontal force and a variable horizontal force. Determine the value of t when the forces acting on the particle are in equilibrium.
So, what kind of scenario would this be in real life?
Jesus.
So that's my question. It's like, so
a
what's
small
this?
a billiard ball is
Yeah.
moving on a smooth horizontal surface with a constant horizontal force and another one that's variable. So you're on a table, you've got a constant force, maybe like it's got a fan blowing it constantly.
Yeah.
And it has a variable force, which could be like, it couldn't be someone hitting it. It could be like another fan. You've got 2 fans. One of them's
Okay.
on constant speed, and one of them's on a variable
somebody's
rate.
moving the other
Yeah.
fan. Okay, so now
There
we've
we
got
go.
like it centered in real life. Okay, so right, the first one then, and this looks quite complicated initially, but I'm sure it'll be fine. So, determine the value of t when the forces acting on p are in equilibrium. Okay, so equilibrium, that means that the forces are balanced.
Yep.
And I'm just going to do it as a bit of a diagram. So here's particle P. Now the constant horizontal force, so it's 8I minus 8I, so that's going west.
Yep.
Minus 54J, so that's south. So it's basically like southwest.
Yeah.
Isn't it?
Yeah,
So
yeah. It's,
if I
it's
just,
very, yeah.
it's
I
like
agree with
something a bit like this.
Yeah.
Okay. Now if it's an equilibrium, that means the other, I'm going to call this FC to be my constant force.
Yep.
And that means the variable force at that time must be equal in size and opposite in direction. So like that.
Mm-hmm.
And I would say if it's an equilibrium, that FC plus FV is equal to 0. So the sum of those two forces is 0. So there's no
Yep.
net or resultant force.
Yep.
Right. So now, so FC, so that's this one here, isn't it? The 8I minus 8I minus 54J.
Yep.
So I'm going to write that as minus 8I minus 54J is FC.
Mm-hmm.
I'm going to add that to FV, which is
4ti
4ti plus 6 times 2t minus 1 squared j.
Yep.
Okay, and that's equal to 0, isn't it?
Mm-hmm.
Right. Okay, so I think then there's a lot there because there's i's and j's, but I'm thinking that effectively, however much this is that way, I guess in the I direction, that's going to be the same size.
Yeah.
So I don't even need to think about the j's, because if the i's are the same
Mm-hmm.
size, then the j's must be.
Yeah.
Okay,
Yep.
so that means then I'm just going to ignore the j's. So I'm going to do
I agree,
I'm
yeah.
going to do this, and I'm going to say, just considering the i's, minus 8i plus 4ti is equal to 0.
Yep.
Or 4ti is equal to 8i. I don't need an I on both sides, do I?
No.
Um,
Because you just want the time, don't you?
yeah, and so the
yeah.
time then is just equal to 8 divided by 4, which is 2. Is that 2.00? How does this work?
You would just leave it at 2.
Is
You would just leave it at 2.
Okay, this is...
Yeah.
Right, okay.
I know it pains you to do so. I can tell the
3 significant
pain.
figures, you said. Okay.
It would just be 2, yeah.
Yeah, so after 2 seconds. Okay, cool.
That's it, yeah.
Is that it?
That's it.
Do I need to confirm it by putting... Actually, saying that...
It's an interesting one, right?
Oh, no, look. Yeah, so...
It will work.
2 times 2 is 4. 4 minus 1 is 3. 3 squared is 9. 6 nines are 54.
They are.
Okay. And then you've got minus 54 plus 54. Okay, that's good. So 2 seconds.
But it's, I suppose, in one sense, you're right. The force in the I direction can only be balanced by I.
Yeah.
And sort of from like a mathematical perspective, you could dot the whole equation with the vector j, and I dot j is always 0 because they're at 90 degrees, and you would get that the i's had to be equivalent.
Okay.
Right? So from like a even ignoring all of the physics and just being like from purely mathematical perspective,
Yeah.
you would get the exact same equation you've thought about. But it's interesting because even if you solved it for I, if the J1 for that t value
Yeah.
doesn't give you 0, then they could never be in equilibrium.
Oh, okay.
right? Because both of them have to be 0 at the same time.
Yeah.
So you're right. You only, the fact that it's telling you that an equilibrium does exist is sort of saying you can just concentrate on one and you don't need to worry about the other. And obviously you pick the easy one, which is the way to do it.
Cool. Okay.
But it's nice to see the other one works.
That's good. Yeah, it's nice to have that double. And I suppose if I had a bit of extra time at the end of an exam, I think, is that definitely 2? I'll just, cause sometimes you do like 4 divided by 8 when it should be 8 divided by 4, and it's like,
I have done that many a time, yeah.
And it's a simple thing to catch you out, isn't it?
Yeah.
Okay, right then. So,
we're now told P is at rest when T is 0.
Okay.
Determine the speed of P at the instant when it is moving due north. This is a big 6 marker, so there's probably a bit more going on in this one.
Right, so if it's moving due north, does that mean... It's not as simple as it's not as simple as there's this constant force on it. So Fc, and the other force is. It's not necessarily that the forces are acting north either, is it?
No, I think it's the total motion of the particle.
So it could still be moving north, even if the forces weren't pushing it north at that point, because it. Okay.
The other one almost certainly couldn't be. If the other force was north,
yeah,
then. Right, it would sort of be going that way in a bit. If you combine them, right, it's like the resultant force, I think. Right?
Yeah, it's almost like even if like
it would kind of have to be. Yeah.
So if the variable force was there, that means effectively. Oh no,
that would make it go left.
Okay, ignore that. Right,
But,
so
yeah.
Right, so we want to know the speed. Okay, give me a clue. How do I start this one?
So I think my first thought would be to use the new piece of information they've given us. In a way. So the fact that, and I'm sure you see this in physics exams, when you're going from part A to part B, the new thing we've been told is that it's at rest when T is naught.
Okay.
So let's try and figure out what does that mean, given that we know the two forces.
Yeah.
We've drawn them in the first diagram, so sub in T equals 0, and what does that actually tell us?
Okay.
Would be my personal starting point.
Okay, so what I'll do then, I'm going to copy this. This is an advantage of using an iPad, actually. I didn't need to write it all out again, so I'm going to copy that. I'm going to put it down here. Okay, so this is the force acting on it, yeah? Okay.
Yes, that's your total force, yeah, exactly. So rather than necessarily being equal to 0, we could call that F.
Yeah, so I'm going to call that, here we go.
Yeah.
Hopefully that makes sense on the video. So this is the force. It's at rest when T is 0, but we want to see how much is it sped up by. So I think here there's a mass of 2 kilograms. Is that important? So we know the mass. We know it was initially at rest. Okay, let's just go in F equals ma.
Yeah.
So Newton's second law. Well, special case of Newton's second law for constant mass, uniform acceleration. Okay, so if you want to work out the acceleration of that object, it's equal to the force divided by the mass. And if we know the acceleration, and we know that maybe it started at rest, we could work out how quickly it's going after a certain time. Is that right? Something like that?
Yes. So this is maybe where it's slightly more mathsy.
Yeah.
What's the relationship between the acceleration we get from Newton's second law, just acceleration, and sort of this idea about it being at rest? Like, that's giving you information about its velocity.
Okay, so I would say that so velocity is related to its acceleration, isn't it?
Yeah.
And also its displacement.
Yes.
And if you differentiate x, you get v. If you differentiate that, you get a with respect to time. So if we know the acceleration, we kind of want to go backwards. I don't know if it's really backwards, but that kind of one step. If we know the acceleration, we can work out the velocity. And if we know the velocity, we can work out that.
Yes.
So rather than differentiating, we've got to integrate, which I did once a long time ago. Okay, so let me work. I'm going to write down the acceleration. So the acceleration is going to be this force here divided by the mass, and the mass is 2.
Yes.
So if I divide all of that by 2, the acceleration is minus 8i minus 27j.
You forgot to divide by 2 on the 8.
Oh yeah, that's not a good start, is it? Okay.
Yeah.
So it's minus 4i minus 27j plus 2ti plus 3 times 2t minus 1 squared j.
Yeah.
Now, to be honest, that looks ugly because there's like i's and j's all mixed up. So I'm going to rewrite that. We've got 4i plus 2ti. So I'm going to write that as 2t minus 4i.
Yep.
I always like it so it's not a minus and then a plus. It's nice to have a plus
I
with
agree.
a minus.
Yeah,
Is
definitely.
that standard maths, or is that just keeping it neat?
It's obviously an equivalent statement, but I would agree. The convention usually is to put the positive things first. It looks nice.
And then we're going to get the j terms together.
Yeah.
Now we've got 2t minus 1 squared minus 27. Now I'm going to write that as plus 3 times 2t minus 1. And then you've got 2t minus 1 minus 27j. I guess that's all in brackets, isn't it?
Yep.
So that's the same then as 2t times 2t times 3. So that's 4t, that's 12t squared.
Yep.
And then we've got minus 2t minus 2t, which is minus 4t minus 3. So that's minus 12t.
Yep.
And then we've got a minus 1 times minus 1, which is plus 1 times 3. So we've got plus 3 minus 27.
Yep.
Which is the same as minus 24.
Mm-hmm.
Or minus 24. It's quite messy, my work. So okay, so that's the acceleration, right?
Yes.
But we want to know the velocity. So, right, integration then. I suspect people watching this, if you're doing A-level maths, you'd be like, that's easy. But we integrate, oh, I see. So we integrate like 2t, and then we integrate 4.
Yes.
And then we integrate, okay, so each of these is like a separate thing.
You can integrate term by term, absolutely. Yeah.
Okay, so say if y was equal to x, if you integrate both sides, what do you do?
You normally have.
Oh, that's too easy, isn't it?
Maybe it would be dy by dx equals x.
Okay, so
right, so derivative is equal to x.
Yeah. So y would be equal to. I think you raise it up by a power and divide by something.
Raise the power by 1 and divide by the new power.
Okay, so
That's
that would
all
then
you'll need,
be x. Well, it's not x. Well, it's x squared.
Yeah.
Divided by 2.
Exactly.
I remember this, and this is like. How many things do you reckon you've derived in your entire career?
Oh God,
how
hundreds of thousands probably. I don't know. Thousands, definitely thousands.
Okay, so I think again, like the quadratic formula, I haven't done any integration really since I left university, which is shocking, isn't it? Oh my gosh.
Am I right in thinking there used to be more of this in A-level physics, but there was a change in the syllabus recently?
Yeah, so there used to be a lot, I think probably, in the good old days, when everything was harder and, kids these days don't know they were born.
Yeah.
In the good old days, there was a lot more integration and
Okay.
differentiation.
Yeah.
But I think now, because there's not a requirement to do A-level maths alongside A-level physics, I think it's seen as a bit unfair that, there's quite a lot of knowledge and quite a lot of practice to get to this point. And I think with A-level physics, the good thing about it is that you can do it as maybe your third, you don't have to do A-level physics to become a physicist. You could do it maybe alongside biology and chemistry if you wanted to go and do medicine at university.
Yeah.
Because if you want to do medicine, you have to do chemistry. That's the big thing.
Yeah.
Biology is quite useful, and physics could be really important if you're going to do stuff on like medical physics and diagnostics in the future. So there is scope to do it as your third A level without doing A level maths, because it's just a nice bit of science to look into. So so integration differentiation has been taken out. As a teacher, I've not actually used much of it really, apart from a bit of stuff with simple harmonic motion and things.
Right.
Okay, so with that in mind, I'm going to apply that to this bit up here. So, right then, so I'm going to move to a different colour. It doesn't really make any difference, I think it's nice. So if A is that, then V is going to be the integral of this, so 2t. So that's going to be t squared over 2. So that just becomes t squared.
Yep.
Minus 4 is then going to be minus 4 times t to the power of 1, so that's minus 4t.
Yeah.
Okay, so that's I.
Mm-hmm.
And then we've got 12t squared becomes, well, that's going to be t cubed over 3.
Mm-hmm.
So it's 4t cubed.
Yeah.
A lot of the actual maths is It's just like multiplying 2 by 3, like really small numbers like being multiplied together,
It's just
isn't it?
knowing what differentiation
Yeah, that's the
integration
problem,
is,
isn't
isn't it? Yeah.
But once you know that, then that's all. Okay, so then we've got 12t, so that's 12t squared over 2, so that's 6t squared.
Yep.
Minus 24t.
Yep.
Okay, and that's j. Right, what next?
Now, there is one small thing which...
I saw you do this in the video, I think. And it's the plus c, isn't it?
Yeah. Just have to be careful, because if you integrate,
Yeah.
any constant will always differentiate to give you 0.
Okay.
So when you're reversing that process, you have to just remember to add on a constant.
Yeah. Okay.
But we have a piece of information here that tells us when t is 0, the velocity is at rest.
Okay.
So if you substitute in t equals 0...
So I'll do that. So so v equals 0. So that's going to be equal to 0 when t is 0.
Yeah.
So t squared. So 0 minus 0. So that's basically 0 i's. Plus we've got a 0 and a 0 and a 0. So plus 0 j's.
Yeah.
Plus c. And that means c must be 0 in this case.
Yeah.
That's nice, isn't it?
So yeah, so even if you'd forgotten, it wouldn't have mattered. But I think it is important to stress that in theory it should be there, but it happens to be 0 in this particular example.
And is that the thing that people forget all the time?
All the time.
Okay,
Yeah.
right.
Plus c.
Okay.
Remember your plus. There's so many memes. Remember your plus c.
It's a whole this maths world is like a whole other subculture of society, isn't it? Okay, right. So, but that's just the velocity, isn't it? And determine the speed at p when p is moving due north. Okay, so when it's moving due north, then I is going to be 0. Is that right? No. Yeah, there's going to be the component of velocity in the I direction, go east or west, is 0.
Yes.
So in that case, the velocity v, so that's going to be 0.
Yeah.
So we can say that t squared minus 4t is equal to 0.
Yep.
That all it is. And then I can just say that t squared is equal to 4t. They cancel. Is that right? No.
Mm-hmm.
So
Well, we know
equal...
technically you should worry about t being 0, because that would make the equation true.
Okay.
However, we know it's not happening at t equals 0, because we're told it's at rest then.
Okay.
So it's not moving at all at t equals 0.
Yeah.
So even though that would satisfy the equation, that there's no motion in the I
So
direction.
t could be 0. Oh, I see. So it's like t could be 0
Or 4.
or t is 4 when I is 0.
Exactly.
Okay, that makes sense.
But obviously, we don't want it when it's t equals 0, because there's no movement at all.
Yeah.
So you're like, ignore that one.
Okay.
So it has to be t equals 4. Yeah.
Okay, so t is 4, but we want to know the speed. Is that right?
Yes.
So if we know t is 4, we kind of put this back into this bit up here
Yes.
to find what that is.
Yes.
So the velocity then, okay, so 4 times 4 times 4 times 4, I would just back it straight to the calculator.
You are allowed a calculator, so
Okay.
yeah.
So 4 times, so that's like the same as 16 squared.
Yeah.
What's 16 squared?
Oh, no, not squared.
Oh, is it not?
Oh, it is. No, it is. Sorry, yeah, my bad.
Sorry, that's like 4
Yes.
times 4
Yeah, times 4 times 4. Yeah, my
Oh,
apologies.
256.
Yeah.
I'm going to write this all down.
Yeah.
Then we've got t squared times 6, so that's 16 times 6. Do you know what? That's not, minus 96. I could do this all in my calculation in one go. Minus 24 times 4, that's minus 96. So is that equal to... I know I could do this in my head, but I'm not. I'm just going to rely on a calculator. So that's 64 metres per second. Is that right?
Yeah.
Cool.
Yeah.
That's a pretty quick
Yeah.
ball going across the table being blown
Yes.
by fans. Okay, so what
We
what
may have the
scenario
wrong-
would this
yeah.
be now?
Maybe a ping pong ball.
In a
so it's
warehouse
incredibly
with
light.
massive jet engines pushing it.
Oh, no,
Yeah.
because it weighs 2 kilograms.
Oh,
Yeah.
okay.
Incredibly powerful fans.
Okay, right. Okay, no, do you know what?
Or maybe it has an engine.
Yeah. Okay, so that one's good. I'm happy with that now, but I wouldn't have done it without remembering how to integrate.
Yeah.
Okay, the next one then. So
Last one.
yeah, this last bit. Okay, determine the distance between the positions of P when t equals 0 and 3. So I'm thinking because we were looking at speed, now we're going to go to distance. There's going to be another integration.
Exactly.
Right. Okay. So what I'm going to do, I'm just going to copy this. So this is v then. So we're going to integrate again to get to x, because dx by dt is v.
Yep.
So this should be easy now. So it's so that's going to be t cubed over 3.
Yep.
Minus 4t, so that's t squared over 2, so that's 2t squared.
Yep.
I.
Mm-hmm.
Plus, that's going to be t cubed over 4, but that's 4, so that's just t cubed. Sorry, t to the power 4.
Yep.
Minus 6t squared, so that's going to be 2t cubed.
Yep.
Minus 12t squared j plus c. So I've integrated it. I've got a plus c. I would say when t is 0, we don't. I guess that's its starting point, isn't it? So because we want to go from between time 0 and 3, whatever its displacement is at time 3, take away its displacement at time 0. That's going to be the distance travelled between those times.
Yep.
So that means we don't actually need to work out c, because we're effectively doing x at time 3 minus x at time 0, and the c's would kind of take each other away. That's explained in a really non-mathematical way, isn't it?
I think so, yeah.
Okay, so when t is 0, x is going to be equal to 0 minus 0 I plus 0 minus 0 minus 0 j. So effectively, when time is 0, x is 0.
Mm-hmm.
But when the time is 3 seconds, the value of x is going to be equal to 3 cubed over 3, which is 3 squared, so that's 9, minus 2 times 9, so that's minus 18, which is, I'd say that's minus 9i.
Yep.
Plus, I'm going to work that out on my calculator. I'm sure I could do it. So t to the power 4, sorry, 3 to the power 4 is 81, minus, that's going to be 2 times 27, so that's minus 54, minus 12 nines, which is 108.
Yep.
So that's minus 81. Okay. So it's minus 9i minus like 81j. So that's basically something like this, isn't it? So if that's minus 9 and that's minus 81. But we want to know the distance. So if that's time 0 and that's time 3, that's just Pythagoras, isn't it?
I think so, yeah.
A squared equals b squared plus c squared, or a variation of that.
Yep.
So, let's see, 81 squared plus 9 squared, square rooted, is 81.498, so 81.5 metres.
Perfect.
Is that the answer?
That is the answer.
No way.
That almost seemed too easy for 5 marks, didn't it?
Is that really 5 marks? Because
that was 5 marks, yeah.
I think the most challenging thing was part B, because we had to use integration to go from whatever it was, from whatever like the force was to the acceleration, back to the velocity. But going from velocity to distance,
it's just the same thing again, yeah.
And that seemed quite easy. Well, not easy, but it was a similar method to the second part.
Yeah, no, looking at this even as a mathematician, I'm sort of intrigued as to how in part B you had to do the integral, but then there was like a second part to the question.
Yeah.
Right. You then had to like figure out, what was it you had to do? You had to do the integral, but then you had to figure out the correct value of t to sub in.
Yeah. Yeah.
But then it was like, we're going to give you the values of t, and you just do the integral, and then it's like, oh, we're done, and yet you get almost as many marks.
I think what helped actually was drawing the diagram, because it's going from the I and the J things to trying to visualise it, thinking, okay, well, if it's along a little bit and then down a lot, then... And
it's not going to be much more than the 81.
Yeah, it's going to be... An 81.5 is almost the same, so... Yeah, okay, right.
So I'd say...
okay, yeah.
Yeah, I think you've done incredibly well on the 2 physics-y questions.
Okay, so that was like the mechanics part of the paper, wasn't it?
That was the mechanics part. And of course, the first half of the exam is the maths part.
Okay, yeah.
So I've got something again, I hope. Well, there was a little bit of integration there that we got to remind you about.
Yeah. Okay.
But yeah, I've tried to pick one that hopefully is quite approachable, let's say, but is different to the kind of thing that you are used to as a physicist.
Cool.
So it's a graph sketching question.
So we do graphs in physics quite a lot.
Okay.
We tend to, I guess we have some weird shapes, so a graph can mean something. So, for example, it could be like the phase change of something. You have the triple point, or there's maybe the graph of resonance or something. Mm-hmm. But we also use like y equals mx plus c quite a lot.
Yep.
So that's like a physics thing. Mm-hmm. But okay, so let's see what we've got.
Number 4 is the one I think we're going to have a go at. So, So it asks you, for the first 2 marks, it gives you 2 equations, and it's asking you to sketch them on the same diagram.
Okay, so the first one is y, is it the modulus?
Yes.
Of x, and that's basically any positive value. So here's my axis. So I would say like, that's y equals x. Mm-hmm. If you had like y equals x minus 1, would it be something like that? Yeah, because that's the intercept, isn't it?
Yep.
Okay, but if it's a modulus, it can't be anything down here, so these values are then like positive. Okay, that looks a bit messy, doesn't it? So
I like how you constructed it though. Yeah.
Yeah, there we go. Right, so that's the first one.
Yep.
Now the second one, y is equal to k over x.
Now I really don't like the notation they've used here.
Okay.
Because they've said y equals k over x, where k is a negative constant.
Oh, do you know I didn't see that? I was going to say like
just helped you out. So, because normally when you, and I don't know if this is true in physics, normally when you see a constant like a k, you're like you assume it's positive, because if it wasn't, you put a minus sign in front of it.
Absolutely, yeah.
So that's why I don't like the way they've done that.
Okay, so I know what a y is proportional to 1 over x is, because this is maybe if you were to plot maybe pressure and volume for like an ideal gas. So I suspect if it's negative, then that bit's going to be down here, and that's going to be up there. Mm-hmm. So it kind of looks... Right, drawing a curve is not so easy, so let's have a look at this.
Nice.
Something like that.
That's very good. Very good. I'm impressed.
Yeah, okay, right. Okay.
A lot better than mine. I always feather my graphs and get shouted
at. Oh, really? Can't do that. Can't do that. That'd be losing my... Okay, so I reckon something like this. So sketch on a simple diagram, that single diagram. Yeah, so that's kind of what I think.
Looks good to me.
Okay.
Looks good to me.
Cool.
And then part B sort of follows on very nicely, because it says, hence explain why this particular equation has exactly 1 real root for a negative value of k.
So I can see if that's equal to that, then that's what we're saying here is x minus 1. The modulus of that is equal to k over x.
Yep.
And that's effectively where this is equal to this. So that's where the 2 values of y must be the same, which is this bit here, isn't it?
Yep.
Now, these lines are never going to cross, because that's always positive, that's always negative, like below the x-axis.
Yep.
And that would only cross in one place, wouldn't it? So there must be only one point. And so what do we mean by real root?
I'm not worrying about complex numbers. So, for example, saying like, could x be a complex number?
Okay, right.
So,
Is that like I? Is that the other kind of I? Is it like
yes, that's the other kind of exactly. That's
okay,
where
right.
I is the square root of minus 1. So I think the reason on some exams you might not see it say that. It might not say exactly 1 real root. It might just say 1 root.
Okay.
But I think here it's important to clarify, because there will be students taking this who will have studied complex numbers.
Yeah.
And they might worry that there could be other solutions to this equation.
Okay, cool.
So, yeah.
Right. Now, I've seen the next one. Okay, determine the real root of the equation. X. Okay, so this is where we're saying that x minus 1 is equal to minus 6. Okay. Now, does that act like a bracket, the modulus symbol? Like, can we say that is the same as x squared minus x is equal to minus 6? Or is that something that I can't do? Like, do you see what I mean?
So you said something very key when you drew the graph, and you were looking at the modulus, and you said it can only ever be positive.
Okay.
So what that, if you just sort of just concentrate on the x minus 1 with the modulus.
Yeah.
So what that's telling you is plug in any value of x, So if x is bigger than 1, then of course it is just the same as x minus 1.
Okay.
But if x is less than 1, what if x was negative?
Okay, so say for example x was equal to -5.
Yeah.
Then x minus 1 would be -6. Okay.
And then if you take the modulus of it,
would then just be 6.
would then be 6. However, so if you were to just take it as you sort of initially thought of, let's just pretend it's just like a bracket.
Yeah.
If you do x minus 1, you get -6. But
Yes.
with the modulus sign, you're getting 6.
Okay.
So it's not quite as straightforward. So you actually need to consider the two cases.
Right. Okay.
So you have to say, first of all, you're going to consider what happens when x is bigger than 1, and what happens when x is less than 1.
And I guess that's because we're sort of looking at this point here, aren't we? So
that's the key thing to it, yeah.
So we're kind of thinking of it as in there's this point where x is bigger than 1 and x is smaller than 1.
Because, again, when you drew the graph, so to the right of it, how would you what line is that?
So that's y equals x minus 1.
Okay, but then when x is less than 1, that's not the same line anymore, is it?
No, so it's going to be...
So you split it up into those two cases.
Okay, so we're looking at this line here. Oh, that makes more sense. Okay, so the line there is y equals... It's going to be a minus x.
Mm-hmm.
But now the intercept... Well, if that's 1, that must be 1. So it's going to be y equals minus x plus 1.
So it's actually exactly the negative of the whole thing.
Oh, okay.
It's exactly what you did from that step to that step.
Okay, so minus x plus... So basically what we can then say is if... Do I treat it almost like a bracket then? So x times minus x plus 1 is equal to minus 6.
That's one case. And then the other case was the one that you did originally up here.
Okay, so that's where...
There are two different equations.
Oh, I see. So this actually then would be minus x squared plus x is equal to minus 6.
Yeah.
Which I guess would be x squared minus x is equal to 6. So x squared minus x minus 6 is equal to 0.
Mm-hmm.
I can see where this is heading now. I've not done this for a long time. Okay, so we've got the double brackets.
Nice. I was going to say, you could also use the quadratic formula, which
could
we know
you?
you don't like using.
No, because I can't remember what it is. That's why it is. So this one then. Okay, so they must multiply to give minus 6 and add to give minus 1. So that's x minus 3. Is it an x plus 2? Just checking that. So you've got x squared minus 3x plus 2x, which is minus x. Minus 3 and 2 is minus 6.
Yep.
So to make that 0, either x is equal to 3 or x is equal to minus 2.
Yep.
But it's wanting the real root of the equation. But we know that x must be smaller than 0. So it can't be the positive one. So I see. So like the positive one would be if this line was to continue.
Yeah.
Down there. So it can't be this one.
No.
So it has to be that one. So x equals minus 2.
Mm-hmm.
Yeah. Oh, that was deep inside me. That knowledge. I haven't.
So
it might be that my method is
not
like
to
poor.
curb your celebrations, but you should celebrate. That was awesome. However, there is now I don't know whether you did this by accident or on purpose, but up here, your original thought was to say, well, if I just treat this as a positive bracket and expanded it out, and then I sort of said, oh, you have to be careful because there are two cases, and obviously you've taken the negative case and we've solved it and you've got the right answer.
Yeah.
But why do we ignore this case? When is it true that the modulus of x minus 1 is just x minus 1?
That's when x is greater than 1. Yeah.
Exactly. And so looking at your graph, you already know that, sure, you could sub in and do the algebra, but it's not going to have a solution because there's no intersection there.
Oh, okay.
So I think you maybe did it by accident. I don't know,
but do you know what, actually, by the graph itself, it's a bit like kind of drawing a diagram or a force diagram somewhere else.
Yeah, absolutely.
As soon as we were talking about this, and I was thinking about what would the line look like, where would it continue? There's a reason then why that. Yeah. It's like pictures, aren't they, graphs? they're like pictures.
Brilliant.
I think we should call it there. I'm gonna
Yeah,
put
I
it
mean,
on
go
the
out on a
head.
high. That was like, you've just
Yeah.
taken a maths question involving modulus and things
But-
and quadratics, and you factored it really nicely. Like,
And I must admit, looking at some of the other questions out the corner of my eye, I think because I haven't done this recently, and like years ago I would have done this and gone, yeah, no problem at all.
yeah,
And now it's weird how like when you haven't been practicing something for a long time,
yeah.
you forget like the little bits. And
It's like any
What it
skill,
means,
right?
yeah.
If you don't practice,
Absolutely.
that skill, you're gonna become rusty.
Absolutely, and if after like 20 years or something of not doing that, it's. However, I can see the relevance for a lot of the maths in, especially like high level, like university level stuff, like undergraduate study, and that could be like maths or engineering or even computing and other kind of things where you need to have that appreciation of the maths to unlock many other subjects.
Yeah.
Tom, thank you so much for today.
You're welcome.
I really enjoyed that more than I thought. I was a bit kind of like nervous doing an A-level maths because I know that a lot of people watching this who see my A-level physics videos, they'll be all over this because this is like their bread and butter. They're doing it day in, day out. But yeah, I actually really enjoyed that.
Well, I'm glad to hear it.
Thanks so
I also enjoyed my version, which again, we're going to remind you to go and watch the first one if you haven't already, where Lewis gave me some physics questions. That's how the challenge started, and this
Absolutely.
is how the challenge ended.
So thank you so much. Again, like if you want to go and see that video and see the other things that you've done with many other people actually, and some other different exam papers and things, have a look at Tom Rocks Maths and subscribe there after you've subscribed here.